CHEM200L to activity 14. A couple of things to note. Again, the activities, just like on campus, the idea is for you to continually work on them until you get to the right answers, till you understand all of the concepts. So many of you have been coming to office hours to do that. Some of you have emailed about that, so that's still an option. You don't just have to turn it in one time to see if you get it all right or not. You can come get feedback. Experiment 8 coming up May 18th, and I know the big experiment is still out there. Experiment 7 post-lab is due May 20th. So a couple of notes. Things are wrapping up, people. Activity 14 and activity 15 is the last activity. There are 9 experiments, so experiment 8 and then one more after that. And this is the exam 3 that covers the last activities and experiments from the last exam. I'll go over that in another video. And then there's one other exam in the future, the lab report exam, but this is the last exam over experiments and activities. So today's topic, if you can just look at right away, there's a lot of equations and really a lot of definitions, because it's not just enough to know the equation is delta E equals Q plus W, but you have to know that this is internal energy, this is heat, this is work. Okay, so there's a lot of things that go with this. I'll go into more detail on enthalpy and endo and exo, and you've seen this equation before, Chem152, but we'll talk about how to distinguish between these equations. Make a comment about delta T, and then one of the problems in particular involves this little more complex heat expression, so we'll talk about that today. First, this is thermodynamics. Okay, we've been seeing Bound's chemical equations for quite some time, but now the piece is that they are associated with a delta H of an equation. So right away we want to look and notice if it has a negative sign, it is exothermic. If it's positive, it's endothermic. So that's one thing we want to recognize right away. The other thing is that this is negative 483.6 kilojoules, and that's an extensive property. That means that depends on how much you have. So if you have 2 moles of hydrogen, this is how much heat is released. What if you had 4 moles of hydrogen? Okay, wait a minute. It's exothermic. It's going to be even twice that. So this is used as a conversion factor if you had some other amount. Okay, so this is the key with these thermochemical equations, is then being able to write it as a conversion factor. Okay, the other thing is to notice what happens in these equations. So here we spent so much time on this bonding theory. That's oxygen double bonded to an oxygen. That's an O2 molecule. Well, what is this? This is breaking up these bonds. This is bond energy. Okay, a term that we've talked about, bond energy. But the real takeaway I want you to see from this is to go from O2 molecule to individual O atoms. That's endothermic. That takes energy, that takes heat to break that up. And now you can look, well, wait a minute, look at the states. So the substance is the same, water on the left, water on the right, but it's going from a liquid to a gas, so that's evaporation. Okay, again, a process that you've seen, but now we're putting it into this thermochemistry chapter. That's also endothermic. And now look here, we've switched this. The water gas is the reactant, the water liquid is the product, and is actually the opposite. Okay, so that's the opposite process. So if that process above is endothermic, then this definitely has to be exothermic. So the first part of this activity is looking at some equations, chemical equations, and determining do we need a ratio, do we need to flip the sign, and how do we address that. The next set is going to be for sure more calculations. Okay, so what I want really to emphasize here is that when we're talking about enthalpy, we're talking about delta H of reactions, and that is the heat at constant pressure. Okay, so that's Q subscript P. This is enthalpy. This is the heat. Okay, that's what this is associated with. Well, now you've got equations for this. Well, heat equals mc delta T. I know that. I've seen this before. What I'm emphasizing here is that the C is in some term of heat per mass per temperature. Could be Kelvin, could be degrees C, but that's the specific heat capacity. And you can see then that's why it has to be multiplied by T. That's why it has to be multiplied by mass. And if you do that, then you get heat with the units of joules. This is a little bit different. This is called the heat capacity. So in the chapter 9, this is mentioned for constant pressure calorimetry, and this is mentioned for constant volume calorimetry. Here we're also applying this in this activity to constant pressure, and it's in regards to the heat capacity of a calorimeter. Okay, so a calorimeter is calibrated, and it's determined that you put a substance in there, the temperature goes up, and the temperature, the heat capacity, it changes the heat per degree Celsius. So these are the units of heat capacity. I know it's so annoying. They're both C's. Sometimes you see this as a capital C, but it can be a little confusing here. But they're both in relationship to heat, so we need to be clear which one are we using. When you're going to use delta T, many of the problems give either the constant or the temperatures in Kelvin. It doesn't matter if you're in Kelvin or Celsius when you're doing the change in temperature. What I mean by that is, let's take 25 degrees Celsius and delta T minus 0 degrees Celsius. Okay, so that delta T, should be a delta T, is 25. Okay, so now let's do this in Kelvin. So that's 298 Kelvin and 273 Kelvin. So this isn't a super exciting calculation because it comes out the same. Here's what I'm trying to emphasize, and here's the problem. If you take the delta T in Celsius and then you add 273 to it, you do not get 25, okay? So the delta T is 25. It is not 298, so either convert both temperatures to Kelvin if you want to be in Kelvin, or just know that the change of Celsius and the change of Kelvin are the same number, so that's 25 and 25. So the most complex problem on this activity is here on number 6. What I want to emphasize is that there's 3 terms, okay? So we break that up, that's the hard part, 3 terms. The heat of the alloy gets put into the calorimeter was calibrated, there was also water in there, so now there's 2 terms where that heat is going. So this is a Q equals mc delta T of the alloy, and this is a Q mc delta T of the water, and the Q calorimeter is actually a Q equals C delta T. So a couple of things, the final temperatures are the same for all of them. Okay, it's all coming to the same equilibrium temperature. The temperature change, actually, for the water and the calorimeter, because that's in the same, those delta T's are the same. So it's just seeing here now there's 2 terms where the heat is going. So this is activity 14. Please see me if you want to go over any of these questions.